Okay. Okay, it's my pleasure to welcome to our department seminar. It's my pleasure to introduce today's speaker, Taylor Norton. Taylor hails from the nearby hamlet of Middleton, Wisconsin, which I just reconfirmed. I forgot that it was that close. I knew it was somewhere close. And she earned her BS in atmospheric science from our department in spring 2020 after the COVID lockdown abruptly and mercilessly crippled her senior year in college. However, this occurred only after Taylor earned a distinction that may never be surpassed, as she is the only graduate student I've ever had who I also saw on the Kohl Center scoreboard at a Badger game once. So that was very choice, I must tell you. I had to tell her the next day. I think I told you the next day. But luckily for Taylor, this is not the only way in which she's distinguished herself here as a student. After graduating, she began working as a graduate student at the Antarctic Meteorological Research Center. She'd been a student hourly there before. She's made 2 trips now to the South Pole, a much more exciting distinction. And in the fall of 21, returned to begin pursuit of her MS degree, research on the nature of the austral-winter, polar, and subtropical jets, and work that's recently been published in Weather and Climate Dynamics. So without further ado, Taylor Norton will tell us today about trends in the waviness of the Southern Hemisphere, subtropical, and polar jets.
Thank you so much, John, for that introduction. So yes, as you mentioned, I'm going to be talking about specifically and also the trends of the waviness of the Southern Hemisphere, subtropical, and polar jets. Just to go over a brief outline of what I'll be talking about, first I'll introduce jets in general and the Southern Hemisphere jet climatologies, as well as the climate modes and their effects on the jets. I'll go over the data and methods that follow the procedures of Martin in 2021, and then go into the results of the jet's waviness, strength, equivalent latitude, and then also some of the connections to SAM and the differences in the wavy seasons. And then to end, I will go over the discussion and conclusions of my thesis. So just a very brief introduction of jets in general. The weather and climate is heavily influenced by the jet streams, and they are meandering bands of strong winds in the atmosphere near the troposphere. 2 prominent jets exist in each hemisphere, during the winter season, the subtropical and polar jet streams. The polar jet stream forms via eddy momentum flux convergence related to the development of mid-latitude baroclinic waves. And the southern tropical jet stream forms from the angular momentum transport via the thermally direct Hadley circulation. Due to climate change and the warming temperatures in the troposphere, the jets are changing their behavior. The Arctic amplification is a coined term by Francis and Waviness, 2012, and they suggested that the undulatory behavior of the Northern Hemisphere jet stream could be linked to this amplification of the warming temperatures and the changing behavior of the jets. And the land-sea differences between the Southern Hemisphere and the Northern Hemisphere are quite different, as you can see in this map, and just in general, but you can see there's far more land in the Northern Hemisphere than in the Southern Hemisphere, and that does have effects on the jet's behaviors when you compare the two, and that the Northern Hemisphere jets are much more variable than the Southern Hemisphere. And the thinking and thought of this is that what happens to the Southern Hemisphere jets in their waviness. And so the thought is that they would, both the subtropical and polar jet streams would become wavier due to the climate change and warming temperatures and the increased latitudinal temperature gradient. The subtropical jet climatology, it has the strongest winds in the austral-winter and is stable around 30 degrees south. And you can see in this image here from Genoli that the strongest the strongest average zonal wind is just off the coast of Australia. And it is statistically significant, increasingly, the velocity is increasing by about 0.6 meters per second per decade in the past 50 or so years, or from when the study was done. And the southern tropical jet stream winter velocity averaged around 45 to 65 meters per second, with the winter months having it increasing by 0.3. Oh, sorry, totally skipped over. The increased concentrations of greenhouse gases have expanded the Hadley cell and therefore have moved the subtropical jet poleward, and it has done so by 0.3 degrees per decade from the end sub reanalysis and 0.1 degrees per decade from the 20 ACR data set from Ortiz. The southern tropical jet also increases in its zonal index, indicating that the jet got wavier, and this is from Gallego, and I'll go over a little bit more of what that means in just a little bit, but it did seem that it got wavier. For the polar jet stream, it seems to move poleward in the austral-winter, and it ranges in speeds from 40 to 55 meters per second. The velocity has increased, although minimally, from 1958 to about 2008, and it was around 0.3 meters per second per decade that it shifted, or increased. And the jet has areas of weakened jet core strength south of 40 degrees south. It also showed no significant trend in the zonal index, therefore seemingly not changing in its waviness patterns from 1958 to 2002. Some of the connections between the Southern Hemisphere jets and SAM, the Southern Annular Mode, is shown here. And just to go over what SAM is that it has the most impact on atmospheric variability poleward of 20 degrees south, and it's related to the oscillating of the geopotential heights between the mid and high latitudes. Winter months in a positive phase of SAM tends to shift the polar jet poleward and increases the velocity up to 50% over the Pacific Ocean, while the subtropical jet shows a slower average velocity in the positive phase and moderate latitudinal changes, but there was a slight equatorward shift seen. And in a negative phase of SAM, the subtropical jet is stronger with higher velocities over the Indian Ocean in the West Pacific. In the decades prior to 2000, the Southern Hemisphere jets shifted poleward, and the SAM has tended to positive polarity. And these are coincident trends that have been presumed to be a result of ozone depletion. But as the ozone recovers in the Southern Hemisphere, as we have seen, the simulations of the jets seem to be shifting. Suggest that the jet's poleward shift in positive SAM polarity may reverse with the recovery of the ozone. Now for some connections to ENSO, the El Nino Southern Oscillation. ENSO is a climate pattern that oscillates between cool and warm phases of the surface temperatures across the equatorial Pacific Ocean. The El Nino phase for the subtropical jet generally has a equatorward shift in the Pacific sector, while the polar jet stream shifts poleward in that same area. The jet strength of the southern tropical jet was the most significant ENSO effect, with the speed of the jet was 25 to 50% larger in El Nino versus La Nina over the Pacific. The polar jet had the opposite effect, where it decreased in speed during El Nino by 10 to 25%. In the Indian and Atlantic sectors, all of the changes are weaker and opposite in behavior. And though these are all true, they are weaker than the SAM connections. There have been previous jet waviness findings, but only one that we could find from Gallego. And so his algorithm was, in order to find where the jets are in the atmosphere, was to identify the 200 hectopascal geostrophic streamlines of maximum average velocity in the Southern Hemisphere. And the maximum velocity of these streamlines show that there were two maxima seasonally, and therefore two jets in the Southern Hemisphere, the two that we know, the subtropical and polar. And in computing the difference between the maximum and minimum latitude found each day for the jets gives the zonal index. And so that's where the zonal index had come up prior, where it was found in here in this map. You can see the subtropical jet has a slight increase of waviness, while the polar jet did not show such thing. There was a similar metric employed by Barnes for the Northern Hemisphere, but this metric does not comprehensively account for the waviness created by the full collection of troughs and ridges around the hemisphere that routinely characterizes the jets. So, due to the possible links of storm track variability, climate effects, and other changes in weather patterns, the waviness and trends of the waviness of both the subtropical and polar jet stream need to be assessed and understood, and doing so in a different way previous studies have done, like the one I just talked about by Gallego. And so we're also looking to see looking to find the austral and wintertime waviness of the Southern Hemisphere, subtropical and polar jets, and the general climatologies of the jet's behaviors. And these findings are also compared to the Northern Hemisphere results presented in a previous study by Norton in 2021. First step in finding where the jets are located in the atmosphere, from the theory that we follow, is identifying where they are in potential temperature and potential vorticity space, followed by the objective method from Christensen in 2017. The Northern Hemisphere jet cores are found on the equatorward side of the strong PV gradient in certain isentropic layers. And the quasi-geostrophic potential vorticity equation can be used to justify this PV gradient and jet relationship. And obviously, here's the QG-PV equation, where phi is phi is the potential. Sorry. After using that equation, we can sub in the natural coordinate expression for geostrophic wind, and the cross-jet gradient of the QGPV can be shown as such, meaning from this equation that the maximum in the cross-flow gradient of the QGPV are co-located with the maxima in the geostrophic wind. The data that we used was the zonal and meridional winds, as well as the temperature at 6-hour intervals from 3 different reanalysis data sets. The first one was the Japanese 55-year data set. We used a total of 62 austral-winters for June, July, and August from 1958 to 2019. And the data was thus, we used 60 vertical levels up to 0.1 hectopascals on a horizontal grid mesh of 55 kilometers. The second reanalysis data set was the National Centers for Environmental Prediction and National Center for Atmospheric Research, the NCEP and NCAR data set. And we used the same months of data, but at 17 isobaric levels to 10 hectopascals on 2.5 degrees longitude grid from 1948 to 2019. The European Center for Medium Range Weather Forecasting, CMWF, reanalysis and AIR5 was the last data set that we used, and using 137 vertical levels from the surface to 80 kilometers with a grid space of 31, covering the time period of 1979 to 2019. So the first step in identifying the isentropic layers that house the austral winter jets is to find at which layer the maximum speed was observed in each grid column and each analysis time in the winter months from the JRA55 data set. And then the use of the isentropic space here is actually differs from Manny et al. And Manny and Higlin, which employed separate latitude and elevation criteria to differentiate between the southern tropical jet and the polar jet. But we actually ended up using the JRA55 data set because of the length of the series, as well as the horizontal and vertical resolutions compared to the other data sets we also use. In finding the maximum wind speeds, the corresponding theta values at those wind speeds, we use GEMPACK to find that data. And the data files that we created from using different scripts and such to get the data that we needed would be the latitude, longitude, highest wind speed per day, the potential temperature at that wind speed, each day of the data and the time. Only grid columns that had an interval average wind speed exceeding 30 meters per second in the 100 to 400 hectopascal layer were considered, following the Koch et al. 2006. The results that we got show 3 maxima in the distribution that are the 3 jets following these isentropic layers: 305 to 320, 340 to 355, 395 to 410 Kelvin. And you can see these here in these humps. But this last one here is most likely the polar night jet And as it lies in the lower stratosphere, it is not a focus of this analysis. So we were swimming the constraints on the layers from Gallego results that implied that the subtropical jet peaks near 30 degrees south, and the polar jet peaks near 50 degrees south. The latitude bands that we set to 0 and 40 degrees for the southern tropical jet and 40 to 65 south for the polar jet, and further analysis of these shows that the isentropic layer of the subtropical jet to be 340 to 355 Kelvin and 310 to 325 Kelvin for the polar jet. And these results are consistent with previous studies as well. So you can see the polar jet is going to be in blue and the subtropical jet is going to be in red for all future figures in this presentation. But you can see that the subtropical jet is the most dominant jet in the Southern Hemisphere, and that is also consistent with prior analysis. Oh, and the 58 or 53.8% of the columns in the Southern tropical jet then were in the 340 to 355 Kelvin layer, and the majority, 46.8% of the columns for the polar jet, were found in its following layer. Next, we need to find the waviness, then that involves circulation, which requires contour length. And a fair comparison among the different data sets requires an adoption of a uniform grid spacing. So all three data sets were bilinearly interpolated onto isentropic surfaces at 5K intervals and 2.5 degrees latitude-longitude grid spacing. For both jets, the average zonal and meridional wind speeds, as well as the average PV, were calculated from the 4 times daily data. Considering that the quasi-geostrophic potential vorticity following Cunningham and Kaiser demonstrates that the local maxima in the cross-flow gradient of QGPV are co-located with maxima in the geostrophic wind speed, and in the Southern Hemisphere, the jets lie on the high PV edge of this PV gradient. Since jets are always in the regions of strong PV gradient, a proxy for the axis of maximum wind speed, aka the core of a jet, is one of the several isotels within the strong gradient region, and a core isotel can vary each day. The goal is to quantify the daily departure of these core isotels from zonality so that we can assess the waviness of each jet. And so using the circulation equation, where C along the isotels of negative 0.5 to negative 5 PBU in each day, in each jet layer every day. The isotel where the average U per unit length is maximized is considered the core isotel as a jet core proxy. Core isotels, this figure is the objectively identified core isotels in black, and they lie very near or at the center of the analyzed isotech maxima around the hemisphere with physically defensible exceptions. In the figure B here, this red dashed line shows this part of the jet core, where this shows the polar jet and D shows the subtropical jet for the black outlines. And so it looks to be that they overlap where the maxima is. And so both, you can see it in both the subtropical jet overlapping the polar jet maxima, as well as in D where the polar jet overlaps the southern tropical jet. The final step in this analysis is to calculate the equivalent latitude, and this is inspired by the method from Huang and Nakamura in 2016. The core isotel on any given day within a certain layer encloses a finite area, and the equivalent latitude is the northern extent of the polar cap, whose area is equal to the area enclosed by the core isotel, and is given as such, where RE is the radius of the Earth. The meridional departure of the core isotel from its equivalent latitude is measured at each longitude, and where the core isotel crosses the same longitude more than once, so where it would be particularly wavy, the segment which has a larger PV then the one north of the equivalent latitude, or vice versa, is counted. The average latitudinal displacement, the ALD, is the sum of all departures divided by the number of longitude lines at the resolution of the data and is converted into degrees. If the ALD were to be 0, that means it is perfectly zonal, and anything larger than that, the greater it is, the wavier it is. So the results of the jet waviness, immediately you can see that the polar jet stream in blue is wavier than the subtropical jet. It is also, the polar jet has become wavier over time, and from this we use the JRA55, so we have 1958 to 2019. And it statistically significantly was increasing by 0.17 degrees per year. The subtropical jet also became wavier, just at a smaller rate of 0.005 degrees per year. And the waviness of the polar jet appears to have 3 regimes, which you can see from these lines marked here. And in this scenario, I'm just going to briefly go over the first 2 instead of the last, but the polar jet decreases at first by 0.024 degrees per year, and then switches to an increasing time period. And the southern tropical or the subtropical jet increases in the first section and decreases in the second, which is interesting to note. The one thing is that none of these are statistically significant, but the closest to being is the polar jet in the middle part here, where it increased. The daily ALDs, the waviness, for 1999, for the Southern Hemisphere subtropical and polar jet, for each data set is plotted here. More than 93% of the subtropical and polar jet ALD seasonal time series are correlated with magnitudes less than 0.3. So this strongly suggests that the 2 jets evolved independently with respect to waviness. And this low correlation between the waviness of the 2 jets in this example year represents the rule and not the exception. Identifying the waviest and least wavy winters, or winter jets, since 1958 is where we sum the daily departures from the calendar day average, ALD, over the 92 days of each winter season. And so here you can see basically the level of waviness for each jet each year. And the overall waviest polar jet occurred in 1991, and the least wavy was in 1977 for the polar jet and the subtropical jet. In 2002 had its waviest year, and in 1964 had its least wavy year. So. Similarly to the Southern Hemisphere, the Northern Hemisphere polar jet is wavier than the subtropical jet, with both jets systematically becoming wavier over the time series. And you can see here, this is all of the data sets in blue, the variations of blue and red, while the Northern Hemisphere is the gray underneath.
Could I ask, please, for a positive equivalent latitude increase, does that mean that it's toward the South Pole or toward the equator?
If it's increasing in latitude, it's going poleward.
So I would suggest an interpretation of these curves is that the amount of polar air or extratropical air is shrinking with time, because at equivalent latitude, you could have a disk, and if you expanded it, then that would go toward the equator. You'd have a lower equivalent latitude. The area would be larger, but there wouldn't be more waviness. So I think this is related to air masses. I thought waviness was related to sinuosity.
No, this is a better measure than that.
Well, so I'm confused because I'm probably wrong. My understanding of Nakamura's idea is that you remap air masses into an equivalent disk, and if it's bigger, then that means there's more of that type of air mass.
All we're doing here is we're figuring out what area is inside the core isotel.
That's what I'm talking about.
Let me finish my response. Then there'll be an equivalent latitude there, and you measure the distance of the isotel from that equivalent latitude around the hemisphere. And then all you do is report the average. And since that core isotel has a physical meaning, which is the core of the jet, you can say something about how wavy the jet is. There may be alternative ways to interpret it, but that's all we're saying here.
If you take a blobby region and then map it into a single area, the former perhaps has more waviness, and the equivalent mapping has zero waviness. It's all equivalent disk, right?
Right.
So if the mapping onto a larger area just simply gives a bigger area.
The areas are the same. There's no larger area. The areas are the same. That's how you calculate what the equivalent latitude is on any given day. It's the equivalent area, just configured differently.
I'm sorry, I thought it related to the spread of cold air masses.
No, not in
that
this,
would be bigger.
not in this case, no.
All right.
All right. So, as we were saying, that the Southern Hemisphere polar jet stream, or the Southern Hemisphere polar jet is wavier and is trending faster than its Northern Hemisphere counterpart. And the subtropical jet in the Northern Hemisphere is actually wavier than the Southern Hemisphere subtropical jet, but they have increased at about the same rate per year. The average wind speed along the chosen core isotel on any given day represents the average jet core speed for that species on that day. The Southern Hemisphere polar jet speed has increased by 0.0039 meters per second per year, which is not statistically significant. And the Southern Tropical jet has increased 0.43 meters per second per year, and that is statistically significant. The average speed for the subtropical jet is about 48 meters per second, and the polar jet is about 33 meters per second. The polar jet the daily average speeds extremes have a minimum of about 31 and a maximum of about 35 meters per second, while the subtropical jet was a bit faster with a minimum of 45 and a maximum of about 51 meters per second. The subtropical jet curve, this figure shows the daily average, or the seasonal, I'm sorry, so the seasonal jet streams, or speeds, and so you can see the subtropical jet curve starts at about 46, plateaus a little bit, peaks at 49.1, but ends at 47 meters per second. And the polar jet begins at a stronger speed, and then throughout the season it dips down to 27 meters per second. The polar jet in both hemispheres show almost no trend in the jet core speed, and any slight change that is seen is not statistically significant. The Northern Hemisphere polar jet averages about 6 meters per second faster than the Southern Hemisphere polar jet. The Northern Hemisphere subtropical jet does not increase or decrease in speed over the time series, and that's statistically significant that it does not, unlike the Southern Hemisphere subtropical jet. The Southern Hemisphere subtropical jet is overall slightly weaker and has less interannual variability than the Northern Hemisphere subtropical jet. The equivalent latitude of the jet is a close approximation to the zonally averaged position. The polar jet equivalent latitude has increased. It shifted poleward about 0.65 degrees per year, and the subtropical jet has also shifted poleward at about 0.2 degrees per year, both of which these were statistically significant. And the average polar jet equivalent latitude was 44.96 degrees south, and for the subtropical jet, it was around 29.72 south. The subtropical jet starts the winter at 28.73 degrees, and the seasonal figure, the seasonal cycle for the winter, and it slowly increases or shifts forward and plateaus around mid-June. The polar jet shifts equatorward at a greater range than the subtropical jet throughout the season. The polar jet starts at 48.8 degrees south, sort of plateaus around late June, and then shifts again down to 42.4 at the end of the season. Comparing these to the Northern Hemisphere, the poleward shift of the Southern Hemisphere polar jet is occurring 3 times faster than the subtropical jet, just like in the Northern Hemisphere. The poleward movement of the Southern Hemisphere subtropical jet is statistically significant, while the Northern Hemisphere is not. The Southern Hemisphere subtropical jet is located at a latitude roughly similar to the Northern Hemisphere throughout the time series, and the polar jet is shifted about 4 degrees further poleward during the winter than the Northern Hemisphere. More systemic and dramatic poleward migration of the two jets in the Southern Hemisphere winter as compared to the Northern Hemisphere. Connections to SAM. We wanted to see if there was a connection between the jet waviness and SAM. And the SAM index here was calculated by projecting the daily 700 hectopascals geopotential height anomalies poleward of 20 degrees south onto the leading pattern of the Antarctic Oscillation of Gong and Wang. The appearance of a positive trend over the time series in SAM seems to be reflected in the increase of the ALD, or the waviness. But the correlation between the two is low, and that suggests that there is no relationship between them. However, we were still curious, so we kept looking. In the 3 winter months with the most positive and most negative SAM streams since 1979 were examined. And the core intertales of the polar jet stream from the JRA 5.5 analysis for each month with each of these months were plotted. And so the positive extremes of SAM in the first column show a clear poleward movement of the polar jet stream, while negative extremes suggest the opposite. And there seems to be no systemic connection between the extremes of SAM and the waviness of the polar jet as quantified by ALD, however. Looking at the differences in the wavy seasons, we took the composites of the geopotential heights at 500, 250, and 50 hectopascal to look at the top 5 wavy and least wavy top 5 wavy and least wavy jet seasons, and they were used to create differences between them. And the difference was calculated by subtracting the geopotential heights and the least wavy composite from the waviest composite. Negative anomalies, or anomalous heights for the polar jet are suggestive of a negative SAM, and that can be seen here with the polar jet. This first one, in the strongest polar jet negative anomaly occurring near the Cape of Good Hope may imply a weakening of the zonal winds in that area. So that would be over here. The subtropical jet has similar spots, but with positive signs suggestive of a positive SAM. The similar patterns between the 500 and 250 hectopascal levels suggest equivalent barotropic structure in the troposphere. So you can see here from leveling up in the atmosphere between the two, but again, they just show opposite signs, but pretty similar pattern. At 50 hectopascal, the difference fields imply that the strength of the polar vortex is influenced by the waviness of both jets. For the polar jet, the height field suggests an anticyclonic circulation anomaly over East Antarctica in its wavy years, and with such a flow, the strength of the vortex could be compromised. Wavy years for the subtropical jet in the height fields imply a diminished and displaced polar vortex, and it appears that an unusually wavy polar jet or subtropical jet would have a weakened Southern Hemisphere polar vortex compared to normal. In the discussion part, the annual June, July, August jet strength increased results are similar to previous studies, and the poleward shifts of each jet agree with the previous results as well. Maher had a similarly dynamic definition of the subtropical jet, but found no evidence of a poleward shift of the Southern Hemisphere wintertime subtropical jet. We suggest that the emphasis on empirically identifying a core isotile rather than the maximum gradient of theta on a predetermined isotelic surface, i.e. 2 PVU as a dynamic tropopause, and that may account for the difference between the Maher study. As there are no other direct comparisons with the way that we found jets defining waviness of the Southern Hemisphere jets, this project outlines the first results of how the waviness jets have changed in recent times. Positive SAM phase is becoming more frequent due to the increased greenhouse gases, and that correlates to a poleward movement and increase of strength in the polar jet. The subtropical jet has the same trends, but a positive SAM phase normally has seen an equatorward shift and decreased velocity in previous studies. Another difference is the circumpolar vortex strength with the positive phase, but the increased waviness of the polar jet does not match with that behavior. During an El Nino phase, the subtropical jet becomes stronger, which may have implications on the waviness or lack thereof during such a phase. The synchronization of coupling of climate modes between multiple and so Pacific decadal oscillation, the Northern Atlantic oscillation, and the North Pacific index provides a marker of a shift in the state of the climate. And it was noted that there are about 5 times when the synchronization had occurred when the climate system distinctly changed between all these years. And the waviness of both jets appear to have 3 regimes marked by change in the latter 2 time periods, which is what I had talked about, where the jet had increase and decrease in waviness in the beginning time series, were in the middle. And it lined up with these synchronization of coupling of climate modes. So some of the conclusions is that the results demonstrate that both of the jets in the Southern Hemisphere have become systematically wavier over the past 60 plus years. And since the 2 jet species are uncorrelated, both in the Northern Hemisphere and the Southern Hemisphere, this suggests that the 2 jets do not influence one another throughout the winter. Both the Southern Hemisphere and Northern Hemisphere polar jet exhibited no significant trend in their average speed over the time series, and the Southern polar jet is notably slower than the Northern Hemisphere. The subtropical jet in both hemispheres have similar speeds, but the Southern Hemisphere jet has undergone a systematic, statistically significant increase since about 1960. In the Southern Hemisphere, both jets have shifted poleward at a statistically significant amount, the polar jet moving about 3 times the rate that of the subtropical jet. The Northern Hemisphere only had the polar jet have a statistically significant poleward migration over the time series. I'd like to have some acknowledgments for the NSF for funding this project and my work with the AMRDC, and so thank you to Matthew and the team. And a huge thank you to my advisor and the committee members, so John, Angela, and Hannah. And thank you. Do you guys have any questions?
Thank you, Taylor. We'll start with questions from students, as is our tradition. Hamish.
I'm intrigued that you're plotting reanalysis data back to 1950 before 1980. It looks like a lot of your trends occurred before 1980, the satellite era. And I'm wondering how confident you are in those results when there was very little observation of the Southern Hemisphere weather prior to 1980.
That is a very good question. I mean, you can only be so confident when you don't have observations, but it is all we have to really go off of. And so I think with at least, every so often they come up with at least new reanalysis. That's also why we used multiple to compare and see the difference between them. And since they seem at least pretty consistent, I have decent confidence in that accuracy at least.
Rudra.
Very interesting talk. Taylor, quick question about the correlation between the 2 species of the jets, and I wonder if there's not a direct correlation. Could it be possible that one jet could be leading the other jet, like there could be a lag or lead correlation if possible, or if there's no influences even at that time scale?
I don't know if you did it in your analysis for your thesis, but we did it all the way to day -5 and day +5 lags, and there's still no correlation. Okay. So there's at least within a 10-day window around the time at the center of a potential, I guess a decision about what day you want to center around. There's no particularly strong correlation in the waviness. So they evolve separately even over that 10-day window. Yeah. Ian.
I guess going off that kind of that same idea, I'm wondering if there is some sort of like lag relationship between the Southern Hemisphere and the Northern Hemisphere. Maybe if throughout one season, Southern Hemisphere waviness is really high. Do you see a response in the Northern Hemisphere the next season? Something along those lines?
I didn't look at that. Have you
Yeah, I was
looked
gonna
at
say,
that?
that's definitely an interesting thing to look at, but we did not do that.
Yeah, no, I didn't look at that.
Yeah.
Libby's working now on extending this type of analysis through the warm season in the Northern Hemisphere, so there may be a way to interrogate this with a little more confidence, if there is actually a signal. Finish.
One feature often talked about in Southern Hemisphere is the split jet downwind of Australia. And I wonder if in your spatial plots you can have any intuition of how this is affecting that climatological split jet of when the polar jet dives southward downwind of Australia. And are we seeing a change in that? Is it becoming more intense, or have you seen anything of that nature in your plots?
I am not sure. I guess since we focus mostly on the winter jet, I don't know if that is seen more in other seasons or if it also is the split jet is seen in the winter as well. It's a good thing to look closely at. I don't know if John has noticed, but.
Yeah, no, I haven't looked at that in our work. It's gone beyond what Taylor did either, so we haven't thought about that.
I have one methods question and one broader physical question, if I can ask both. Could you clarify the earlier method that looked at waviness and how that motivated needing a different metric? I think I got lost in what's new about this method and how it might impact your results. Because it seemed like a takeaway from this is depending what method you use, you get different trends. Or did I misinterpret that? Could you just clarify a bit more about that?
Yeah, I could definitely try. So is this what you were talking about with the previous?
Yeah, so what was kind of lacking and what did you build off of with
yeah.
the method?
So in this case, they used the 200 hectopascal geostrophic streamlines, and that was just the only way that they found jets was at that level. But I feel like the jet could be at different levels, I think, as well, not just at that one level. And the way that we found it, at least, it found it in a different space instead of geostrophic geostrophic streamlines or heights. We use the PV space, and so it would be located in a different area in the atmosphere, comparative at least to what was found using this type of study. Did that sort of help or no?
I think what Gallego did and what Libby Bonds did in 2013 is Gallego found the 200 millibar streamline that was with the maximum wind speed, and then looked at the highest latitude it attained on a day and the lowest latitude it attained on a day, and their measure was the difference between those two. And that was their measure of waviness over the whole hemisphere. So it was from one extreme to the other is the measure. And the same with Libby's work on the 500 millibar height field. It was the day max min, I think she called it.
Yeah.
What's the maximum latitude that a 500 millibar streamline finds on a day, and what's the minimum? And so that only gives you the difference in extremes. In between is a ribbon of waves.
Right.
And so this method that we've been using, I think, finds those waves with a lot more certainty than just the extremes. So it's quite a different method, but I think it's one that accounts for all of the waves that you might find around the hemisphere instead of just the extreme differences.
So that ties into my more physical mechanism question, because they hinted at this trend, right, and that motivated looking at it in this more detailed method. And going back to your hypothesis is that you hypothesized the reasoning behind this was because of an increase in the latitudinal temperature gradients. So that was your initial hypothesis, that waviness was tied to those gradients. So now that you've done this analysis and found all of the different factors that appear to be complicating this story, how does that reflect back on your hypothesis? How would you kind of refine that or evaluate that, physically straightforward one, and now you find the more complexity? Could you just kind of connect those pieces a little bit more?
Yeah, so obviously, yes, it is far more complex than just something so simple like that. And so now it seems that the why it became wavier, it just seems like it may have to do with multiple, although maybe related to the increasing temperatures and the changing of that, but the way that affects the climate modes, and then how those interact with the jets and how they behave.
With the biggest imprint on which mode? Because I know I was kind of writing, and this is where my own, just trying to put all the pieces together coming in. You know, you talked about the Hadley soap, you talked about the SAM, you talked about some other modes. So which one is kind of the dominant feature here?
And so that's what I'm not sure if there's really one that's dominant. I think it's a mixture of modes interacting with each other that might be having an effect on the jets.
Yeah, I have a question. So one of the things you noted in your results was that it seems like your two jets are shifting poleward at different rates. So over time, to me, what that means is they're spreading apart. And I'm just wondering, have you thought about what the sort of dynamical impacts of that would be in the long term, like on synoptic scales or climate scales? Your choice in terms of how you answer that question.
That's definitely a fair question. I don't know if I've thought a lot of that into that type of thing, but with poleward movement, at least with a polar jet, it's gonna at least really keep colder air further in, and there's gonna be less of that in a way. And I'm not sure how to really put that in with them even separating, but yeah, if I can think about that and come back to you later.
Yeah, totally okay.
I can make a comment. We didn't examine this together, but in the Northern Hemisphere, some of the other work we've done on the jet broadly, not just the waviness, has suggested that though there's no systematic influence of one jet on the other, this goes back to Ruth's question, it doesn't happen in a sort of predictable way, but there are incidents where the polar and subtropical jets interact in a fairly substantial way, change the structure and make a totally different dynamical animal that is very often related to high impact weather. So to the extent that the subtropical and polar jets are separating, maybe the frequency of such superpositions goes down in the Southern Hemisphere compared to what it was 50 years ago. And therefore some fraction of high impact weather events will not exist anymore. What fraction is a good question.
So you looked a lot about, and I know your focus was on the latitudinal shifts of the jet, but you also looked at the core isotope level. I'm wondering if there was any trend in the actual height of the core isotope at the time.
That's a good question. I don't know if I looked at like the height in the atmosphere of the jet cores. I did not look into that, so I'm not sure. But that's a good point.
Yeah, I know that wasn't your focus, but I was.
Yeah.
Yeah, we stayed in the same theta level, but that doesn't mean it didn't move in the vertical.
Yeah,
That's
like
an
if it was at the
interesting
bottom
question.
of that theta level and then at the top.
Yeah, it could also migrate. It's 15 degrees deep, yeah.
Yeah.
So it's a good question. Matt?
I like the result that, I think you said the Southern Hemisphere polar jet in the, I guess, UTLS is a little weaker than in the north. Well, do you have any ideas about why that would be? You know, just a physical explanation. It seems intriguing.
Yeah. So the difference of, sorry, can you say that like the, which part of is different?
Maybe I have it wrong. I thought you said that the Southern Hemisphere polar jet was slightly weaker than the Northern winter. That's true.
Yeah, okay, yeah, that does sound true.
It's interesting. I just was wondering if you had any ideas about why that would be.
Again, another very good question. I feel like maybe I have something, but at the top of my head, I can't quite put it. So if I can get back to you on that one as well, that would be great. Because
No, it seems like a really hard thing to figure out.
It's definitely not part of what study further looked into, but.
I wonder if the continentality difference is a bit of a flywheel for
Something
the
to do
winter
with
time,
it, but
in the Northern
you might
Hemisphere.
think the continent would make it stronger in the Southern Hemisphere, but it's not.
Or in the Northern Hemisphere, I would think. Right, because maybe you have more widespread cold air masses.
North-south displacements and angular momentum transport in?
I never
with
think that way, but
continentality?
maybe, yeah. And then what about this? What are the number of positively and negatively tilted waves? I think that might have something to do with it too. But all of those things are questions that can be taken up. it's a really good, it's a notable difference and worthy of further investigation. Any other questions for Taylor? Okay, well, join me in thanking her again for